I think we've got everything, mate.
Yep, studio's completed, the microphones are in. Yeah,
We've got our outfits.
I've got our outfits, yeah.
Yeah,
We've
big
got our
chain,
pristine
glasses.
white car that never gets dirty somehow.
Yeah, I don't know how that happens, it's great.
It's great. We've got our own film crew. I'll tell you what we do need is a name.
Oh, you're right, we need a wicked name for our sick-ass rap crew.
Yeah, right. Have you got any name ideas?
I think I have one.
Yeah.
I think we could be D2O.
D2O.
Yeah,
oh, it's quite catchy.
sounds good, doesn't it?
Yeah. You know D2O is already a thing though.
Is it?
Yeah, it's really useful in this revision video actually.
Oh, that's handy. So we just talk about that and then later
We'll go
plan
on
our posters. Yeah, okay.
Yeah.
So, first, let's basically explain what D2O is and then how it's useful. So D stands for deuterium and it's an isotope of hydrogen with 2 nucleons.
So because it's an isotope of hydrogen, you know you get H2O, you can get D2O, it's exactly the same.
Yeah. And it's useful because it's got an even number of nucleons, it doesn't show up in the NMR spectrum.
Yes. So where is that useful in spectroscopy?
Good question, well done.
Well done you. It's when we have these OH groups and these NH groups.
Yeah, so if you looked at the at your spread, you'll see that they cover the whole thing.
Yeah. And the reason they cover the entire thing on your, I'll show you just in case you don't know what we're on about.
Yeah.
In your table of values for your chemical shift, it goes all the way across.
They're very broad.
They are. They can change where they are depending on the solvent.
Yeah.
And they're quite wide as it is, so they take up sometimes more than a whole gap of numbers. And so they show up all the way across, and it's really hard to distinguish whether it's other stuff that's underneath it or whether it is an OH-NH group. And so that's where this becomes useful.
It does. So what we can do is you can react this in a reversible reaction which will replace our H's with D's, removing it from the NMR spectrum.
Yes, because remember, because deuterium has 2 nucleons, it doesn't show up at all in the spectrum, so we'll just get rid of it completely.
So if we have something, a carbon chain attached to...
I'll call it R, it doesn't matter what this carbon chain is, but it's got an OH at the end.
It's got a pirate family, that one.
Yeah. It's got an OH at the end.
Yeah, in a reversible reaction with you adding this, D2O.
Add yourself a little bit of, I don't know what it would be called.
Deuterium
Just call it D2O.
oxide.
Maybe. Forms a reversible reaction. And one of these deuteriums substitutes with one of these hydrogens. So you get R to O to D and DHO instead of H2O or D2O, DHO. And because this is now a deuterium instead of a hydrogen, it won't show up an OH group, and so you won't have this massive peak where you don't know what it is.
So what you do is you do the spectrum before and after you add the deuterium, and it will be different, and you compare the differences and what it is.
That's exactly it. And that can be really useful.
It can be really useful, but we should show where it's useful then, with a worked example.
A nice worked example.
You've been hunting again?
I found a nice question, yes.
Oh, that's always a good thing to find.
There's a ton of worked examples in the book over the page from where I'm taking this. So if you struggle with any of them, we haven't said it in a while. Yeah. You can message us questions here on Facebook in the comments below.
Yeah.
Here on Facebook.
Here on Facebook. We're on YouTube at the moment.
We're on YouTube.
You might have seen us on Facebook. You can send us a message on Facebook in the comments, YouTube below. Yeah. And on Twitter, you can tweet us like birds, and we will send you a...
Tweet you back.
You will tweet you back. That's what you said, something quite different there.
No.
We'll tweet you back and give you a full explanation of more in detail how to do a question.
We haven't said that in a while, so
there you are.
So it's question 2 on page 91 if you wanted to find it. It's not a normal worked example with an answer right there. We're going to do an actual question. Okay. On the wrong page entirely. Not on page 91.
Okay, it's on page, drum roll please.
95. Page that this is all from.
That's how you tell.
So, proton NMR spectrum in figure 4 is for a compound with molecular formulas. This is going to be important.
Right.
CH3, H7, NO2. So they really like C3, H7, NO2.
That makes much more sense. Yeah. A bit confused what that was about.
Yeah, good. C3, H7, NO2. And they always give you these molecular formulas in SE, so this is a typical sort of question. Okay. It says, analyse the spectrum to suggest a structure for this compound. So it's got it with the D2O and without the D2O, which is why it's important. So I'll draw both of those up. Yep. So we're going to have a graph with it and a graph without it. And the one with it, with the D2O, isn't going to have these inconvenient peaks. And the one with it without it is going to have the peaks. You can use that and it gives you the integration values like it normally does and the exact chemical shift like it normally does.
Cool, so is this, which one am I going to do?
That one's with D2O.
Okay.
So with, and it's got two things. It doesn't have the large peaks because that's the whole point of D2O. One of them is a quartet and one of them is a doublet.
Okay.
And there's a 2 there and a 4 there, if you remember that. There you go, he's got it. So that's the quartet, it's got 4, and then just below 2 it's got the doublet with 2.
Okay.
And then it shows it without the D2O.
So it'll still have those things there.
So yeah, those things aren't going to change. That's an important thing to realise, is those things aren't going to change. But the thing, that there's 2 peaks that are going to show up all of a sudden here.
So
And one of them's between 4 and 6, there's a 6 here.
okay.
And one of them's between 10 and 12, all the way up here.
Again, there'll be a line here and it'll be up in the air, which I forgot to do, but yeah, I did.
So it shows you, I'll write up this bit, it shows you the exact, for this bottom graph,
Okay.
it shows you the exact chemical shift. Again, it doesn't tell you which one's which, but you just line it up. So we've got 11, we have 5.1, 3.8 and 1.2.
Okay.
And then it tells us your integration, your ratio, 1, 2, 1, 3. Like that.
Okay, so now, again, the first step is always to look at what these things correspond to.
Yes. So I'm going to take it back a few pages as well.
Good.
So, at a chemical shift of 11, or in between 11 and 12, we have the COOH.
Okay, so it could be this.
And then above it, it's got the OH and the NH all the way across the top there as well. That's always there, but we didn't read them out before because we didn't need to. But it's just worth considering.
Yeah.
Perhaps. So in 5.1, so in between 5 and 6, there's the C double bonded to CH.
Okay.
And again, obviously it's got the OH and the NH above it because that goes all the way along. At 3.8, so between 3 and 4, there's O to CH, and then there's halogens to CH, so H to CH we'll say, and of course there's the OH and NH again. And then right at the bottom at 1.2, between 1 and 2, there's an R to CH, and then there's OH and NH again.
Okay, so what we're going to do is we're going to see what disappears and what doesn't, basically.
Yeah. So let's look through it all.
Yeah.
Well, right away we can see we don't have any halogens, so the
that's
halogen
true.
can straight away disappear, which is that one,
Mm-hmm.
H to CH.
And I think everything else is still possible.
It is possible, and that's a lot of things to think about.
That is, but that's why we have our 2 things here. So
Now,
first,
Yep. I was going to say, because there's
Okay.
2 peaks have appeared here, there's 2 separate ones, there is going to be an N group and an OH group, because as it stands here, we weren't certain, although it's probably because of the sort of questions they ask, we weren't certain that there was an OH group at all,
yeah,
because there's 2 separate peaks, one's going to respond to an NH group and one's to an OH group.
yeah,
So we can tell that there's going to be 2.
okay,
That's worth mentioning. But we don't know which one's which yet.
we don't. So let's draw what we have without those. Start with.
Let's think about these integration things as well.
That's very important, remembering it's corresponding to the amount of H's attached to it.
Yeah. So this number 11, between the 10 and 12, the thing that disappeared, so we know it's either an OH or an NH, we don't know which yet, but it's got an integration of 1, so compared to everything else, there's 1 proton in that environment. So firstly, let's add up the integration to see how many different things there are.
Okay.
There's 1, 3, 4, 7. How many protons do we have?
7.
So we can straight away say how many protons are in each of these environments.
Count is a good thing to do there. So that means there must be 1 proton in this environment.
Yep. Just like that, there must be 2 in that one.
Yep.
1 in this one.
Yeah.
And 3 in the final one. So that's a useful step straight away.
That is.
How many protons are in separate things. Now, these can either be an OH or an NH, and we don't know which.
We do not know which.
But this only has 1 proton.
Yeah, so that suggests that it must be an H.
Yeah. So it's probably going to be an OH. We can be almost certain, because the chances that an NH is going to bond to some other stuff twice, so that it can only have 1 proton, is unlikely.
Because often they form NH2 is attached to a C.
Yeah, that's a thing to remember. It's often NH2.
Okay.
And this one's got 2, And we know we've got one NH and one OH, and you're not going to get an OH2, because that's not going to happen.
No, so this one must be our NH2. So we can say that we've got an NH2 somewhere and an OH, and these aren't attached to the same carbon.
Yes, so these are all important factors.
Mm-hmm.
So we know what to do with a quartet and a doublet. We know what's going to be going on. There's going to be some sort of CH3 and some sort of CH, not CH2. Remember, it's N-1.
So each one causing the other.
Yep. So if we've got a CH3
adjacent to this, which causes that, and a CH adjacent to each other, causing the other one,
then we're starting to get somewhere. So let's count what we've got down here and what we've still got left.
Okay, so you've got only one O gone, just need to now have another O somewhere.
Yep. There's only 1, 2, 3, 4, 5, 6. There's all the hydrogens.
All the hydrogens are covered, all the nitrogens.
But there's one more
carbon missing as well.
So a CH3, that's not going to simplify.
No.
At the end of this chain, either end, it doesn't matter, but it has to be an end. There is a CH3. So I'll draw that up. That's for definite.
Okay, there's definitely one of those there. Now it's attached to something else.
It is. Now there's only 3 carbons,
Mm-hmm.
and one of them only has 1 proton on it. So it's probably a good shout to suggest that that would be the central carbon.
It is quite a good suggestion.
So, I mean, this could all be wrong, so I would advise doing either this in pencil, ready to rub out, in case you make a mistake or notice where it could be, or at least have room to then correct it afterwards in your exam.
It's a good idea.
Or, at worst comes to worst, ask for some spare paper and write it on there. So
then you can add your next carbon.
Yep, you know there's going to be a third carbon, and that's going to be the end of the carbons.
So you also know that your N and your O's, OH, aren't on the same carbon.
But the question is the OH here and the NH2 at the end, or is it the other way around?
So what we've got to think about is what do you have missing? Well, we're missing our last O.
We are. And so we're missing this O. If it was, and it's possible, if it was an OH here and an NH2 here, then that means the other oxygen would be here. But it's probably a good suggestion that the OH and the other O are going to go together to make an O to OH, a carboxyl group.
As that is one of our options here, that could be one of the things that happen.
That just makes it a whole lot simpler, because if that is indeed what's going on, then we can get rid of those two for a second. We can say that it ends in that.
And if it ends in that, then our middle must be our NH2.
Now, we've made a few assumptions as we've gone along, and I've been saying, well, that's probably a good suggestion, this is probably a good suggestion. Now, at this point, you check it, and you say, does that line up? Does that fit? And looking at it, it does. So that's why you should do it in pencil, because you might get to that stage and go, well, actually, no, it would make more sense if the NH2 was here and the OH was here, but this is a better way.
Yeah.
And that's a typical sort of question. It's quite horrible. They don't come up that often, actually. The deuterium oxide, getting rid of these things, doesn't come up that often. But when it does, they're often hideous questions with big marks available.
End of the exam sort of thing.
Remember, be sure to look at your ratios between them.
Yeah, it's a good idea. And as Wayne did earlier, it's a very good idea to sort of add them up, see how many it's relation to our hydrogens. Because if it was 14, you'd know that each one would represent 2 hydrogens.
Yeah. And that's all jazzy, really.
Yeah.
That's all the cool
So
stuff.
now that that's sorted out, we need to sort out our rap group, right?
Yeah, so equinox paradox.
No, I thought we sorted that.